Welcome to Part 3 of Control with Wireless.
Okay, I'll start covering kind of really the valve side of this. And so with the wireless valve versus a wired valve, what you have to look at is when you approach that valve, you don't treat a wireless valve any differently in your standard practices as you do a wired valve. When you do the system integration piece of it, you're using wires for the set points and for the feedback. The only difference is on the wireless side, if you're a non-Delta V user, you would use something like a Modbus register, an OPC register, an Ethernet IP register to a PLC. In Delta V, it's native, so it looks just like a standard, any other standard instrument out there. So you don't deal with the registers, and it's a lot easier. The chart over the right talks about how you approach a valve. Typically, the 4 to 20 and the discrete valves out there, they typically are acceptable by customers from a customer point of view of being used in on-off modulating and in safety controls. You know, they've been there for a long period of time, and they've got a track record that people are comfortable with. You start getting into field bus. Field bus has been used for on-off and modulating. They are being used for SIS type of applications. They're probably, less time than the 4 to 20 out there. And so there's some skeptics out there, maybe a little bit on the field bus side, of using it for any and all safety applications, but it is gaining ground. You talk about wireless, it's the newest technology out there that you can use in your toolbox, and for most cases it's used for on-off controls. I've got, it's for some in modulating controls, and the biggest reason why it's some cases is you have to assume that they're not using PID+. As soon as you start putting PID+ in there and handling both the input side of the monitoring side, then you start becoming this into most applications. Our work is to try to get PID+ out into all of the control systems out there, or PLCs, and move the wireless into the same stage as field bus, and then eventually the same as the conventional side. So how do you integrate wireless into your control scheme? And we had a question about that, and you do exactly the same as you do a wired. You've got, your normal PV, SVTVs, your process variables that go into the control system, and the control system's there to manage the process. It's there to meet product spec. It's there to meet availability. It's there to meet, the time to market. All of the things that the control system does comes from these devices into those standard variables. On the other side, you have some type of a maintenance system, asset management system, something that looks at the information coming from the transmitters and field devices and allows you to make better decisions. That talks about the alerts, the cycle counters, how long it took to open the valve, how long it took to close, how hard the valve is working to maintain a set point, or how hard it's working to maintain control. What you want to do is start using this information to know more about that valve and react to valves before they affect the process. And it doesn't matter which valve valve or digital valve positioner out there, they all provide some level of information, and all you have to do is start using some of the easy alerts that are in most of those positioners, like travel deviation, drive signal, supply pressure for a modulating valve, or for the on-off valve, you're going to look at travel deviation, you're going to look at open and close times, and you're probably going to look at cycle counter. Those are typical for the on-off valves. But you look at both sides and you treat them exactly the same, and they look the same in front of the operators. And as you add more devices, they just populate onto the network and into the control system. You talk about applications on the discrete side. There are many applications out there that you can put them on, whether they're a makeup water tank, whether they're a storage tank and you're using it as a drain valve, you're controlling it, you're doing nitrogen blanketing and you're using a valve to keep the blanket there. And this is just really on the discrete side. I've got some presentations that talk about many applications, and you can go out and look at it, and I've got many slides that show all of the applications that you use it for. Typically it's drain, fill, feed, flush, any of those valves you can think of. Now with the control side, you're sending a throttling signal, and so you're sending a throttling set point to there. And it's just as easy as an on-off valve. Instead of sending it a 0 or 1 or open and close, you're sending it a modulating command. The thumb and the DVC 6200, you can actually send that set point from the gateway or natively from the WIOC and Delta V. You can actually send set points to valves. One of the things Terry talked about in our lab was when we did sending a set point to a valve, how long does it take to get down to that valve? And so we looked at this and we talk about a time to apply. And what Terry's looking at with the PID Plus for the input side, we're also looking at a similar type of configuration or arrangement in the PID algorithm to handle the output. Because the PID algorithm needs to know when that valve is going to execute on that command. And so there's things in any communication network, I don't care if it's field bus, Profibus, or wireless, there's some amount of latency and jitter in any of that communication. And so your PID algorithm needs to take account for that. And so one of the things that's coming out is something that's called time to apply. The PID algorithm would tell the valve to move at a certain point in time in the future, and he will have confidence to know exactly that that valve is synced up with that same time and will execute that command at that time, so that when the process variable or process sensors come back with the next update, it knows how long it's been since the valve moved and that update came in. And so really what we're doing with this time to apply and look at all this PID and PID Plus is really taking this right here, where it's used in some cases, to moving it to most cases. And that's really the objective kind of the wireless control valve, is to get into that mode. And then we start looking at some of the control valve examples, and Bailey even went through some of them that she did in the divided wall column that talked about, you know, is it the middle component, the top component, or the bottom component? And they're all being used in a fairly fast process. Questions?
I might have missed this in your presentation, but you have an 8-second lag, I guess, in temperature, 20 points of sample. And then you have an 8-second lag, I guess, on your valve, without any process 16 seconds. Or how is that synced up?
The measurement, let's say it's being updated every 8 seconds. We said the control is going to be executing much faster, though. So as soon as it changes, there's really no lag as such. I mean, what was transmitted is very fresh. So at that point in time, you're seeing what really happened, not 8 seconds ago. You're seeing at that time. It does an output. Now, the time to get out there can take 3 to 8 seconds or longer. I mean, 20 seconds in some cases. So you say, how do I account for that time to go down? And why is that so long? Well, your measurements are scheduled, so they come up precisely at the scheduled time. But downstream is not scheduled, right? And there's some work going on in Rosemont right now in the gateway to support downstream publishing, which is going to help eliminate a lot of that delay. But it's not there yet. Okay, so today you have that delay. So the other thing we're talking about is this time to apply HART command, where you say, I want you to move to 50% in 8 seconds from now. So where it takes 3 seconds to get down, or 5, or whatever, you know in 8 seconds that valve really moved, and therefore in the PID you can actually compensate for that. And so we did liquid flow in the lab with wireless valve, wireless transmitter, and this Wireless Control Foundation book, we have all the results of that in there. So if you're interested, thumb through it at the bookstore, ISA bookstore, and you'll see what we're doing there.
So let's say I have a lot of manual valves in my plant.
Yep. There's actually a couple of ways of doing that. One is we have a position transmitter only that you can mount on top of the valve. I don't care if it's a rotary quarter turn valve or a sliding stem valve, and provide feedback. If you wanted something else and it had very long travel or whatever, you could also use a couple of our Go proximity switches and connect them into a Rosemont 702 and provide that same kind of limit switch feedback as another option. So there's several options out there. So you can connect and attach to every single valve out in the plant if you wanted to wirelessly.
So on your gateways, you currently have, I'm aware of a limitation on 9420s and full spectrum data being pulled back. With the introduction of this new control, are there going to be new limitations on the amount of devices on a gateway that are doing control, things like that?
Oh, with the control, unlike like 9420 uses a lot of data to pull a signature back, and with you do even with the valves, the field view, if you do a valve signature and pull that information back, there's a lot of data to that. But those are typically non-periodic. You might do that once every month or once every 3 months or 6 months. The control features use very small amounts of information, just like the transmitter sending that information up. All you're really sending down in a control signal is, I want you to open, I want you to close, I want you to go to 45%, and the more advanced ones would include that value plus a time to apply. So there's not much data there, and so it really has no effect over the number of devices that are within a gateway.
Just a thought, is that value to run the PID block out of a position, like we do the foundation field bus case, rather than take it back to controller?
You're looking at doing like control in the field?
Yeah, just you have a PID block in your position and then take the.
He was asking if there's a PID block in the positioner, and if I read it right, if a transmitter could send directly to that PID block and speed up the control loop. Is that kind of what you were asking? Okay. And so right now, that is one of the things we have been looking at in the future, but right now, the transmitters all report their data up to the gateway, and then they don't have what we call a peer-to-peer type of communication route where a transmitter sends directly to the valve and the valve executes the PID. We've had PID in smart positioners, but right now the traffic still has to go up all the way to the gateway and then back down to the field. So right now there's no advantage for doing that, because by the time it gets to the gateway and the PID is running almost instantaneously in the PID block, you don't really gain much yet. But it is something we're looking at in the future.
I'm just kind of curious. So you're doing in your test here, you're switching from wired to wireless control. And the wireless control looks pretty good, but it's obviously not quite as good as the wired control. Are you quantifying the difference? Like if someone passing a valuable product in the pipeline, are they going to want to look at the dollars that made up in that difference?
We actually, as part of the UT configuration, we have a module that's just calculating statistics on that, and we didn't show any of that here, but we're set up to do those performance tests, integral valve Solidera, maximum change in valve position, that kind of thing. So it's built in. We just haven't documented all that yet. But yeah, that's a good question, and it's a good idea. One of the things is when you're doing integral valve Solidera, you get sort of a false impression, because if you could actually go to the transmitter and see what's really happening, the fact that you're seeing a step and therefore, it looks like you had a lot of error in between. In real life, that wasn't what was happening, right? And so you actually get a distorted comparison of wired versus wireless. Makes wireless look worse than it actually was in terms of interval of absolute error and that kind of thing. Yeah, so it's an interesting challenge. How do you document that? How do you show that where it makes sense?
You have both on there, right? So you can take
Oh yeah, we can.